And we're back. Welcome back and happy Thursday. Today, we'll continue on with our discussion of the network layer, specifically the data plane. But before we begin, some administrative bits. Homework number 3 concerning the transport layer will be due this evening at the usual 11:59 and 59 seconds. All right, so where we last left off, we talked about longest prefix matching, and we said that to get this prefix matching to happen fast, it is done in hardware using something called content addressable memory, which is what would be implemented in an enterprise-grade router. So the switching fabric is responsible for getting a datagram from an input ports queue to an output ports queue. And it's responsible for transferring a packet from the input buffer to the appropriate output buffer. The switching rate is the throughput, the rate at which packets are moved from the input to the output, and it's often depicted or described as a multiple of the line rate, how fast things go along those individual channels through which the datagrams pass. And so if you have n inputs, you have a switching rate that's n times the line rate is what you desire if you have these n inputs. And so there are 3 basic architectures for switching fabrics. There's a memory-based fabric, so you have your input ports, your output ports, and those datagrams are ushered from the inputs to the outputs using memory as the channel. There's bus-based, akin to what you'd have in the CPU architecture, a high-speed substrate that connects data from an input port to an output port. And then you have something called a crossbar switch, and a crossbar switch can have multiple concurrent pathways between an input port and a different output port. They can operate in parallel. And in that, with a crossbar switch, you can have 3 concurrent pathways going on, and it facilitates that transfer of those datagrams along 3 substrate pathways. And so let's take a look at switching via memory, and this is the approach taken by early routers. Now, of course, this is not a particularly good router, but it nonetheless is a router. And you can still today find special distributions of Linux that will allow you to set up and install your machine to turn it into a router. And so a packet is copied into the system's memory, and the speed, therefore, is limited by memory bandwidth, as well as 2 bus crossings to get from an input port across the memory, and then from memory across to the output port. So you have your datagram comes in, sent into memory, they queue in memory, and then they're taken out and sent to the output port. Another type of switching architecture we describe as a bus. Now, a datagram is sent from an input port's memory, the queue, the buffer space, to an output port using a shared bus. Now, of course, you only have a singular bus. While it is certainly a high-speed substrate, it is a limited resource. And as a limited resource, you have all of these input and output ports contending for access to the bus. The input ports want to have write access to send data, and the output ports want to have read access to receive data. And so you can get bus contention, and the switching speed is limited by the bus bandwidth. So there are products out there that use bus architecture. Well, by today's standards, they're not as popular. Now, then there is a crossbar switch. Now, Banyan Networks created the crossbar switch, or were a very popular computer networking company, and they were purchased by Cisco, and Banyan made something called Banyan Vibes. I remember that. And so Banyan, a crossbar switch, it's an interconnected network, and it did originally different processors in a multiprocessor system. And so we find that in computer networking, a lot of concepts that were used in parallel computing are making their way to computer networks, because after all, parallel computing has very fast substrates for exchanging data transactions quickly. And so you have a design, and you take your datagram, you segment it into fixed length cells, as they're called, and these are switched through the fabric. and they can get much, much higher bandwidth in addition to having multiple concurrent paths between inputs and outputs. And so here in the crossbar switch depicted, this figure on the right, we have a pathway from this first input port to that output port, and then you can have another one, say from here to there, and then that last one from here to there, and they will concurrently run as long as these paths are unique. You don't have two inputs going to the same output port. And so one of the things you can get is so-called input port queuing. And what this input port queuing arises from is that the fabric, switching fabric, is slower than the input ports combined. So that means you're going to have some datagrams waiting or queuing. Now, of course, you can get queuing delay, but you can also get packet loss if your buffer fills up and you get buffer overflow. Now, there's a type of blocking that can occur, and that blocking is because a particular output is busy and two are contending for it. You can actually result in some head of queue item not getting the service that it needs. And so you have a queued datagram at the front of a queue, and it's preventing others in the queue from moving forward because it has to wait. And so in this diagram, we have in the first input port that's on top, we have this red datagram that wants to go to that first output port, the red one. Likewise, down below, you have a red datagram, and it wants to go also to the same top output port on the upper right-hand part of this figure. Now, of course, if they're both contending for access, let's say this first red datagram, it is currently accessing the output port. This second red datagram, the bottom one, it has to wait. And because it's waiting, even if this green output port, that third output port, is free and available, this green datagram that's queuing behind this blocked red datagram in this third input port, that green datagram has to wait because it's not yet at the front of the queue. And this is called head-of-line blocking. And that can lead to slowdowns and therefore having a large queuing delay. And so once this upper red datagram gets to its output port destination through the switching fabric, you now unblock this green datagram because this red one that was head of line before it is now able to go through the switching fabric, and this green is able to get scheduled for switching. And so if we look at the output ports, the output port also has a buffer, and as these datagrams come off the switching fabric, they wait in this buffer for the output port. And the reason why they wait is because when you're transmitting a datagram, other datagrams may be arriving to that output port, and they have to go someplace. And so buffer is required when a datagram arrives from the switching fabric faster than the transmission rate to push them out onto the physical media on line termination. And so the so-called scheduling discipline is used to choose among different queue datagrams selected for transmission. Now, of course, if you have a preference for being selected for transmission, that means your data flow between the source and destination endpoint is going to see higher end-to-end throughput. Now, of course, this is controversial. So-called net neutrality says that you shouldn't have a preference for certain content. And the argument goes that if all data is created equal, there's no preference for one type of traffic versus another, then the internet remains free, and I tend to agree with that. But others on the side of net neutrality say that you should allow switching fabric or ISPs to put in preferences for selecting a certain type of content because you can innovate and get all sorts of new capabilities. And there are many that make great arguments on the side against net neutrality. But I encourage you to look this up because it's really, really important, especially as we go into wireless 5G and 6G beyond that. And so the datagram packets can be lost due to congestion, and they can also be lost due to lack of buffers. And that lack of buffering can happen in the input port queuing, but it can also happen in the output port queuing. And so you can have priority scheduling, and this priority scheduling determines who best gets the performance. And this has to do with network neutrality. Should you prefer or should you not prefer? If you don't prefer, it means everyone gets the same consideration in terms of the datagrams. But if you do prefer, it's not the same consideration. And there are arguments on both sides of this issue. So let's take a look at output port queuing. Now, of course, you have buffering when the arrival rate for packets or datagrams coming out of the switching fabric is greater than the output line speed. And the reason why it might be greater than the output line speed is because it takes time to transmit the bits of that packet, and the switching fabric is usually quite efficient, quite fast. And so you can get queuing delay and also packet loss due to this buffering. And so this is accomplished, this preference, by a scheduling mechanism. And scheduling decision concerns what choice the output port is going to make, or some service is going to make, in deciding which of the waiting requests it's going to attend to, it's going to perform first. And so-called FIFO, first in, first out scheduling, it selects the jobs or the tasks to process in the order in which they arrive to the queue. Now, of course, there are many real-world examples of this, like a bank and like the registrar's office. But nonetheless, if you can get a preference for selection, you're not going to wait as long, and your data is going to be a lot more high throughput, and you're going to realize higher end-to-end throughput. But if you need to make a decision, you have what's called the discard policy. If a packet comes in and the queue is not full, you just add it to the queue. But what happens when the queue is full? You have to make the choice about discarding a datagram. You can either drop the one that just arrived. You can, that's called tail drop. You can do priority-based dropping. So you select based on some rank ordering and you drop the one with the lowest priority. Or you can do randomized. You randomly select some entry in the queue, some waiting task, some datagram, and then you just drop it. Okay. So let's now look at the datagram format for IP version 4. Now, the responsibility of the network layer is a number of things. There's the forwarding decision, and it's encoded by the forwarding table, and that forwarding table is determined by the routing algorithm. And this routing algorithm is driven by a set of routing protocols, and it deals with the selection of optimal paths through the ISP's network of routers that are interconnected in some fashion. And the popular ones are RIP, Router Information Protocol, OSPF, Open Shortest Path First, and BGP, Border Gateway Protocol. And so these routing protocols result in a forwarding table that's set up to represent the path decisions made by path selection. And then you also have the IP protocol, and that deals with how you address or identify unique network cards or interfaces. There's the datagram format, what fields mean what and what is their format, and what responses are taken to various pieces of information in the fields for the header information as well as the payload data. And then there's also how you handle the packets. And then lastly, there's signaling, informational signaling in ICMP, Internet Control Message Protocol, and that's intended for error reporting, to diagnose what's going on the network, get important messages, as well as the router. All right, so this is what the datagram looks like. We have a number of fields. That's the protocol version number. This is IP version 4, IP version 6. Now, IP version 4 has been out for some time, and IP version 6 is an improvement on version 4. You also have the header length, which tells you in bytes how long the header portion is for this datagram. You also have the type of data that it is. You have the max number of hops, or the so-called time to live. And so when you are forwarding a datagram, you want to make sure the datagram doesn't get circulated in infinity, tracing a cycle, for example, in the graph of routers marking a pathway through the network. And so what this time to live does is each time this datagram, layer 3, is visiting a router, the router examines the time to live field, it decrements it by 1, and then stuffs it back into the time to live field on that datagram. Now, of course, once it goes to 0, the router that gets it when it decrements it and it goes to 0, it says, aha, this is no longer a valid time to live. I'm going to kill off that datagram. Now you also have upper layer. This determines to what upper layer, which is a transport layer above the network layer, you should deliver this datagram. It has a checksum. We talked about checksums. And it has a 32-bit source internet protocol or IP address and another 32-bit destination IP protocol or IP address or destination address. And so we have a bunch of options, and then lastly, we have the payload area. This is going to be the segment data in its entirety that's going to be delivered to the transport layer above, whether it's TCP or UDP. And so these are all the different fields. And if we look at the number of bytes, the space taken by these header types, you have 20 bytes of TCP header. That's the header information, not the MSS, the payload. And you also have 20 bytes of IP header information. So totally, you have 40 bytes of header information plus the application layer overhead, those pieces of information that are meaningful to the application layer. And so one of the things you can have when you look at a link for a network, you can have multiple so-called MTU, media transfer unit sizes for each one of the links. And so if you have a router, if you have a network, and that datagram, for example, fits well on that particular link when you transmit it, it might need to change if, for example, you're sending an email from some machine to another machine or some other message like Skype video. Now, of course, you have a media transfer unit, and that's the maximum transfer size for a particular datagram. And if you look, there are different link types, have different size MTUs, media transfer units. So suppose you have a large IP datagram, and this datagram is smaller than the MTU that it encounters when it gets to a particular link. So the only course of action that you can take is to chop up that large datagram into smaller datagrams so that will actually fit in the MTU for the next link. And then you leave them intact as fragments, subdividing them into smaller fragments as needed to match the MTU size for that particular link. And then you don't even reassemble them. You just let them stay fragmented and let them arrive at the endpoint, and it's at the destination endpoint that these fragments are actually reassembled. Okay. And so there are bits then in the IP header that make it easier to mark and manage all of this fragmentation. And so you start out and you have a datagram and you send it to a router, and on the other side of that router is an output and it has a smaller MTU. So one large datagram in this case is chopped up to compose 3 individual datagrams, and each one of them is created uniquely with certain header information to manage the reassembly. Now, of course, these blue regions for the datagram on the other side of the router, those are the headers, and then the red region, that's the data, those data portions on the other side of the router output. Those correspond to 1/3 of the data for that larger packet that was inbound. All right, so now once these fragments get to the destination, they are reassembled, and that reassembly constitutes the entire original larger datagram that was sent. And so let's do an example, and this is from the book, and this is to look at the different flags and what the flags are for IP when you do fragmentation. So let's imagine you start out with 4,000 byte datagram, and the MTU, media transfer unit, is 1,500 bytes. Now, of course, for these 4,000 bytes, you're going to need 3 of them in order to represent those 4,000 many bytes in the intact datagram. So you start out, and the length field in the IP header information is going to be of length 4,000, and you have an identifier, let's call that X, and you're going to have something called the fragmentation flag is going to be 0, and the offset flag is also going to be 0. And the reason why that offset flag is 0 is because when you're dealing with that first fragment is going to be placed, its payload, placed at offset 0 relative to the original datagram payload. And so here, our next big datagram is chopped up into 3 small ones, and these 3 small ones have an MTU, imagine, of 1,500 bytes. And so the length field is going to be 1,500, and then this last length field is 1040. It's 1040 because if we have original 4,000 and you have 1,500, 1,500, that's going to be 3,000. But then also we have the header information as well that you need to account for. And so here in the first fragment, you have a length of 1,500. You have an identifier of X, and your fragmentation flag is set to 1. Now, what this fragmentation flag set to 1 means is that all of the payload in this fragment, in this datagram, which represents a fragment, all of that payload is part of one larger datagram. And so here it says this is a fragment, and the offset where this fragment worth of data is going to go is going to be at offset 0. Now, of course, this completely fills the datagram. Now, the next one is going to completely fill. So you say length 1,500, ID is X, and the frag flag is set to 1, indicating the fact that this particular datagram is a fragment, a smaller part of a larger datagram that started that way. Now, you notice the offset here, the offset associated with that data of length 1,500, that offset is going to pick up where you left off, starting originally at offset 0 in the beginning. And so the next 1,500 minus 20, because 20 of the bytes are header information, so that's a total of 1,480 many bytes of data in the payload area carried by the fragment. And so if we take that 1,480 and we divide it by 8, well, 8 bits to a byte, and you get a total, if you were to express that offset in terms of bytes, it's going to be 185 bytes. And so we set the offset field for the second fragment to 185 because that next 1,480 many bytes is going to start at byte offset number 185, which is bit number 1,480, and it's 1,480 because out of this first 1,500, 1,480 of them is actual data, and the remaining 20 bytes is going to be header information. And so lastly, if we take the 1,480 and the 1,480, that is 2,800 plus 160, that's 2960. And that 2960 is going to be the byte offset for the next fragment's worth of data. But here we have 2960 as the byte offset for the first 2 fragments worth of data, and we have the remaining amount to get you up to that 4,000 bytes. And so if we have the remaining amount, that's 2960 plus 40 is 3,000, and then we have another 1,000 to get to 4,000. So that's 1,000 plus 40, that's 1040. And so here, now, this third fragment, we have a length field of 1040, and out of that 1040, we see that the ID field is X and the frag flag is 0, meaning that this third fragment is not, it's the last fragment in the sequence, and its offset is going to be 370. Now, of course, that 370 means 370th byte in that stream of bytes, and that particular offset, if we take 2960, which was the first 1,480 plus the second 1,480, and we look at that as bytes, that's 370 bytes. And so we start this third fragment at offset or byte offset 370. All right. So this length then is 1040, and that length we said we had 1040 left worth of data, and we started at offset 370 in bytes. And so here we have that 1480 plus 1480 out of 1500. So that's 1480, and 20 of those 1500 bytes are going to be header information, so that leaves 1480. We have two 1480 payloads for the first fragment and for the second fragment, and that 1480 plus 1480 is 2960. Now for this 2960, that leaves us, as we said, that's 40 to 3000. That's 1040 is going to be the amount of payload data for that last fragment. Okay, so we know that 20 bytes are header information. So out of the original 4,000 byte datagram, 3090 of it is going to be 3980 rather, which is 4,000 minus 20 for header. 3980 bytes is going to be the amount of payload. And so out of that 3980, we have 2960 in the first two fragments. That leaves us 1020. Now that 1020 plus that 20 bytes of header information, that's going to be the amount of payload in that last fragment. And so here that length field is 1040 because we have 20 bytes of header and 1020 bytes of payload. All right, so with that, let's go forward. So let's take a look at the addressing part. Now, an IP address, or so-called Internet Protocol address, is a 32-bit address, and this 32-bit address is written as 4 8-bit numbers, and these 4 8-bit numbers are separated by dots and converted to base 10. And so here, a IP address represents a so-called interface. That's a physical connection between a host and the network, and it's typically a network card that gives you this so-called network interface. And so each IP address is associated with a single interface. Down at the bottom, we have an IP address in base 10, so it's 223.1.1.1. So we have 223 in base 10, 1 in base 2 rather, 223 in base 2. We have 1 in base 2, 1 in base 2, and 1 in base 2. And so here in this diagram, we have an example network, and we see here we have very stylized numbers, 223.1.1.1, 223.1.1.2, 223.1.1.3, and so forth. We have another network, 223.1.3.27.223.1.3.1 and 223.1.3.2. And so you'll notice here there's a style that's been adopted. Now we have the most significant bits of this number here. It's 223.1.1. Here is 223.1.3, and here is 223.1.2. And so in computer networking for IP addresses, we often talk of this common most significant bits in this so-called dotted quad representation as being the so-called network address. All right. And so these interfaces are physically connected. In subsequent chapters, we explain exactly how they're physically connected when we look at the link layer and think more about physical layer. But certainly you could spend a whole semester just on link layer and physical layer, which we will not do, and in that amount of detail. And so all of your wired Ethernet connections are connected to something called a switch. And a switch is a link layer construct, and you can think of it as a specialized pass-through that sends that signal information between each one of the links to other links. And so the switch is invisible from the network layer's perspective, and you can think of it almost like a weird kind of conductor, and we'll talk more about what the switch does. The switch only traffics in the physical layer and the link layer, and therefore is called, often in literature, a so-called layer 2 device. And so you have wired Ethernet connections connected together, and they are reachable, can pass one another datagrams without the router storing and forwarding. You need a router when you want to send datagrams to a different network, to machines that have connection to one another, but not across networks. And so a network is defined as a bunch of end systems or hosts that can directly communicate with one another along the same physical wire, or it can be over the airwaves and broadcast radius if you're using wireless and have therefore wireless transceivers. And so here we have a wireless so-called Wi-Fi interface, and a base station is acting like a switch for the devices reachable in your wireless radius. And so for now, you don't have to worry about how interfaces are connected to one another, but you can think of what happens when you disconnect the router. You have these so-called islands of connectivity. And so the so-called subnet part of your IP address is represented as the high order bits, and the host part is represented as the low order bits. And if you ask the question about what exactly is a subnet, it's the set of device interfaces that have the same subnet part of the IP address. That's called a subnet. And moreover, they can physically reach each other without an intervening router to store and forward datagrams. So you only need a router when you're trying to get things to a different network from your network, trying to get datagrams. Now here we see the 223.1.1 network is over here, and we see host number 1 on this 223.1.1. We see host number 2 on this 223.1.1 network, host number 3, and host number 4. Likewise, on this 223.1.2 network, we have host 1, we have host 2, and we have host 9. On the 223.1.3 network, we have host 27, we have host 2, and we have host number 1. And so here we have a network that consists of 3 so-called subnets. We have the 223.1.1 subnet, we have the 223.1.2 subnet or network, and we have the 223.1.3 network. Okay, and so in order to determine the subnets, what you do is you detach each interface from its host or router, and you create these so-called islands of connectivity. Each isolated island is going to be a subnet. And so you can also write these subnets in terms of the number of bits that are meaningful to the network address, and that's called the subnet mask. And so here, for this 223.1.1 network, we see a 0 and a /24. That means the most significant 24 bits, which is the first 3 8-bit digits, those first 24 bits are going to be the network address, and everything that remains, which is 32 minus 24, because it's a 32-bit address, that's going to be 12. The remaining 12 bits are going to be used for the host portion. So this is going to be the network, and in this case, it's going to be the host portion. All right, because here we're dealing with 32-bit addresses. And so here we see the 223.1.2 network with subnet mask 24, and we have the 223.1.3 network with subnet mask 24. All right, so question then for this network, how many subnets do we have? Well, we have this subnet, that's one island of connectivity. That's 1. We have 2. We have 3. And we also have 4, 5, and 6. Let's not forget those. They are networks, and you don't have to have a device connected in order to have a network. Now, of course, there are 2 devices connected. You have a router connection here, router connection here. But by device, I mean an actual host somewhere in the middle. Those are perfectly valid networks. They have a subnet mask, and they have a network address, and they actually have 2 devices. One is a router's connection to the network on one side as well as the other side. All right. So one of the things that used to happen in the early days of networking, they assumed that you had a certain number of hosts on your network when they assigned an IP address to you. There was a so-called class A, B, C, and D network where it referenced the amount of bits you had for host addresses. And so this, we found, we made it so that we would quickly run out of available IP address, and we were, because a lot more devices were coming online. And so here, when we talk about CIDR-ized addressing, classless interdomain routing, we take the subnet portion of an address of arbitrary length, and then we have a format where we have the dotted quads followed by a slash, and X, where X is the number of bits used, uppermost bits used for the subnet part. And so if we said 200.23.16.0/23, that means you have these bit patterns for decimal number 200, for 23, 16, and 0, and the first 23 most significant bits identify the subnet. So what that means is that the least significant 9 bits, because it's 32 bits total, 32 minus 23 is equal to 9. So that means the least significant 9 bits are going to be representing your host address. So there's the network address, the subnet part, and there's the host address, the host part, for your CIDRized IP addresses. And so another question that one might have deals with something that's immensely useful, and this is DHCP, and I had the opportunity to work with someone who was on the Internet Engineering Task Force working on DHCP when I was early in my career. And so typically when you configure an IP address, it's hard-coded on the machine by the system administrator. But oftentimes if you have a lot of transit users, like in the department when we used to be on campus, you open your laptop and all of a sudden it would connect to the network. Well, that connection to the network, in order to participate in a network, you need to have an IP address. And so it is the purpose of DHCP, Dynamic Host Configuration Protocol, to dynamically get an address from a server and then allocate this new IP address to you when you attempt to join the network. And it does so in a plug-and-play fashion where all just happens automatically, just by opening your laptop. And so DHCP has a goal to allow a host to dynamically get its IP address from the network server when it opens and joins. And so this is based on time in the form of a lease, and the host can renew the lease on this address. So it says, oh, let me use this IP address for some period of time. And so after this renewal of the lease for the use of that IP address, it's good to go for another lease period until it gets close to the expiration of that lease that was handed out. Now, of course, this is immensely useful, and there are a bunch of messages that go back and forth. The first is a broadcast by that host that joins. And the reason why it's a broadcast instead of a direct message, point-to-point, using something like TCP or UDP, is because it doesn't yet have an IP address. You can't send data to something that doesn't have an IP address. So the host engages in broadcast, and broadcast is done through a special IP address that lets the system know that, well, this should be forwarded to everybody on the network. And so the host broadcasts a DHCP discover. It says, hey, I need to acquire an IP address for some period of time from a DHCP server instance. And it kind of shouts it to the heavens and the earth to everyone who can hear it or see that broadcast. So one of the entities waiting on the network is the DHCP server. It sees this broadcast, it gets it, it says, I know of some IP addresses that are still available. Let me respond back with an offer letting you know what's available. So these 4, 10, or however many IP addresses are available. So then the host gets it, this list, this response, and says, okay, well, let me request this particular address or IP address from the DHCP server. And so then the DHCP server gets this and goes ahead and sends the address to say, okay, well, here is the IP address, your IP address is, and let's go ahead and mark that off for you, reserve it for you so that no one else can have it. So if you don't renew the lease, the DHCP server says, oh, I haven't heard from you in this period of time. I'm going to allow others to acquire and reserve this particular IP address. All right, so let's take a look at what happens with DHCP. You have a DHCP server running on one network, and you have a host that joins another network, and this host that arrives needs some IP address. So what happens here? You have your arriving client. It sends out a broadcast, and so the network is flooded with your request message, and it says, is there a DHCP server out there? So the DHCP server responds back, but the message that this host or this arriving client sends, it's going to have a source IP address of all zeros because it doesn't have an IP address yet. But it's going to choose a so-called ephemeral port number, because you need a port number in order to engage in communication so that the endpoints will know which application it should go to. And so here we have a destination address that's special. It's all 255, and that's nothing more than 8 ones in an 8-bit representation. And so here, the special address is the so-called broadcast address. And if you compose any message in computer networking and you send it to a network address of all 255, it will get broadcast. And so it asks your internet address is going to be used to communicate the particular offers for IP addresses and transaction ID so that you can identify the particular interchange that resulted in either denial or an acceptance of this connect or allocation of IP addresses. So then the DHCP server broadcasts its response back. Now this broadcast from the DHCP server is not because it can't communicate, but this arriving client doesn't yet have an IP address. And if it doesn't yet have an IP address, well, the DHCP server can't respond back to it because address means that I can contact you. And so it says, okay, well, my source IP address is the IP address of the DHCP server, and the destination address is going to be broadcast. So the DHCP server is going to broadcast this message. It says your internet address is, so that's going to be the offer as 223.1.2.4, transaction ID, so it can identify that particular conversation, and then it has a least lifetime of 3,600 seconds. So then the client says, okay, well, I'll take that IP address. And so it says, okay, source is still 0000 because at that time, while the client that is joining the network, it has an offer, it hasn't yet confirmed it and it hasn't yet received validation that this particular offer it had handed out to you. And so when we send this request message, it's going to use a transaction ID, and you'll notice the transaction ID is very closely related to the original transaction ID. But this time, it's going to have a destination address of broadcast, and it's going to have a port number, and the source is going to be all zeros. And the reason for that is, again, the arrival client doesn't yet have an IP address. All right, so now we have the response. It's going to be broadcasting an OK message. All right, well, I've reserved it. It's now yours. And so at this point, the arriving client cannot install the IP address until it's gotten confirmation from the DHCP server that the DHCP server has actually reserved that IP address for your usage. All right, so we have the source address then is 223.1.2.5. Destination address is broadcast because, again, this arriving client doesn't yet have an IP address. So the DHCP server has to broadcast back its response. And then it sees the response, it picks it up, and it says, okay, let me go ahead and reserve this 223.1.2.4. And it has, of course, a transaction ID, as well as a lease. And so DHCP is immensely useful. Not only can it assign or reserve an IP address for every machine that wants to attach occasionally to the network, it can also assign multiple other pieces of information. One, such as the first hop router from the client, also known as the default gateway. And the other is the name and IP address of the DNS server itself. So it can tell you, hey, not only here's your IP address, but this is the DNS server you contact when you're trying to resolve these host names into numbers. You can also assign via DHCP the network mask, how many bits in the uppermost bits of the address representation are used for the network or for the subnet. Okay, so let's consider a DHCP example. You have a machine on your network and you have a router device that has a DHCP server built in, which is typical for a router you'd pay maybe $100, $200 from Best Buy for. And so your machine connects to the network, and you have your 5-layer stack on the end systems or hosts, and it sends a DHCP request message in order to acquire an IP address. And so it goes down the stack, peeling off each time, makes its way to the physical layer, hits the switch, and now is a new arrival. And so once it comes into this destination endpoint, It goes up its stack, gets stripped off of header information, and then you get back the DHCP request on this server side. And so now this request is responded to, and it sends that ACK back down through the stack on the receiver endpoint, goes through the network, it makes its way back to the client. It strips off the header information for the Ethernet frame link layer, for network layer, and then ultimately transport layer, and making it up into the application layer to DHCP. And so the server formulates the acknowledgement, and it contains the client's IP address and the IP address of the first hop router, so the client knows where to go to send its datagrams. And it also provides the encapsulation of the DHCP server, and the frame is forwarded when it's sent across the network. All right, so the client then knows its IP address, its name, and it knows the IP address of the DNS server as well as the IP address of its first hop router. So it has all the plumbing it needs in order to engage in communication now that this IP address has been installed. And so this is an example, and you'll become more familiar with it with Wireshark, but this is an example of what the DHCP interaction looks like inside of Wireshark. All right, so you can see we have a DHCP request. There's one message. And then we also have the information concerning that requester. And we also have, let's see if we can find it. We have request IP address, hardware type, client MAC address, have a lot of requested name, IP address. Okay, so we have a requested name, and we have a host name. So let's see. So now your client IP address is, all right, and then we also have next server IP address. All right, so now once you get back this information from your DHCP query or DHCP request, you're also going to set other types of information, such as the subnet mask. Well, here's the subnet mask. Here's the default gateway. And then we have some IP addresses. All right. So let's take a look at how to get an address. How does a network get the subnet part of an IP address? And really, it gets allocated a portion of the addresses owned or allocated to its internet service provider. And so let's imagine the ISP had a block of addresses that was from subnet 200.23.16.0 with a subnet mask of 20. And so for the subnet mask of 20, we have 8 bits here, 8 bits here, that's 16, 8 bits here, that's 24, and we take out 4. 1, 2, 3, 1, 2, 3, 4. So that means at this juncture, that's going to be our subnet mask. Subnet. So that's going to be our subnet. Now, given that subnet, whenever somebody orders a block of IP addresses, that's going to be carved out of this ISP. And so if we had a total of 8 organizations, that's 0 through 7, well, how we get 0 through 7 is with 3 bits. So these next 3 bits are going to be used to hand out subnets. Now, if we hand out subnets for these 3 bits on top of that 20 bits, the subnet mask is going to be 23. And so you notice here, 23, 1, 2, 3, is going to be here. So this is going to be the subnet portion, and this is going to be the network portion, or the host address, as it were. All right, so now we have 8 of them. You'll notice we have organization 0 has 0, 0, 0 for these 3 bits. This has 0, 1, 0 for those 3 bits. This has 1, 0, 0 for those 3 bits. And so here, the subnet is just a continuation of chopping up the address space from the ISP's block. All right, and then lastly, up to this last organization, it has last 3 bits, 1, 1, 0. All right, so we can carve out a maximum, in this case, of 8 sub-organizations in 3 more bits above and beyond subnet mask associated with the ISP. Now, the good news is that if this ISP is pretty big, you can subdivide things, and each organization you give out IP addresses to can decide free and clear what they're going to do with these addresses within the block or range of addresses that were assigned to it by its ISP. All right, so why is this longest prefix matching good for routing? Now, of course, if you have different organizations, and let's imagine you have a place called Fly-by-Night ISP. It's actually named after fly-by-night futons in Western Massachusetts, but nonetheless, let's say you have these 7 organizations on their different networks identified by the subnet portion, and the subnet mask for each one is 23 bits, the uppermost bits describing the subnet or the network address, and we have them within Fly-by-Night ISP. Now, of course, when Fly-by-Night ISP's router tells the world around it on the internet, these are the block of addresses that I manage, it's going to give you that whole block 200.23.16.0 with a subnet mask of 20. And so all of those addresses, because they're carved out of that main IP block of addresses for Fly-by-Night ISP, it's going to advertise that block so that others know, okay, if I have a destination address for some datagram, I know I'm going to send it out that link to whichever router told me is associated or manages or switches or forwards addresses that are in this block described by that particular network address. So let's say we also have something called ISPs RS, and it's going to say, for example, send me all of those datagrams in the block of addresses 199.31.0.0 with a 16-bit subnet mask. So that means these first 16 bits are going to be describing the network, and then these last 16 bits, 2 to the 16, is going to be the number of hosts you can have on the network. And so here, ISPs RS is going to advertise, send me any datagram that's within this range of addresses for that particular block. Now, of course, one of the things you can imagine, let's say organization 1 decided to move to this new internet service provider. Now, of course, this block of addresses, 200.23.18.0 with a subnet mask of 23, that doesn't naturally fit, well, it doesn't fit at all, inside of 199.31.0.0/16 subnet mask. And so what happens then in this case, you'd think that, gosh, well, how do datagrams that were originally going to organization 1 when it was in Fly-by-Night, which is underneath this block of addresses, I took this subblock and I excised it and put it on a new network. And so now what the solution is to now have ISPs RS advertise that it also manages this block of addresses, 200.23.18.0 with a subnet mask of 23. Now, of course, the fact that you do longest prefix matching means that the datagrams, even though they might look like they're in this block of addresses, it's always going to pursue that link associated with the longest prefix match from the forwarding table. And so that means is that you're able to move blocks of addresses arbitrarily from one internet service provider to another internet service provider, and the datagrams will find you. All right. So how do you actually get a block of addresses? You go to ICANN, the Internet Corporation for Assigned Names and Numbers, and you allocate the addresses. And it manages the DNS, and it assigns domain names, and also is responsible for resolving disputes. Now, in real terms, it all depends on who has a bigger budget for high-powered lawyers. Now, another construct, which is kind of a violation of layering, but it's immensely important, is called Network Address Translation, or NAT. And what this NAT does, it was meant to alleviate the issue that you only get typically one IP address when you subscribe to a home internet package. And so that particular IP address, it'll be known, for this, in this example, 138.76.29.7. Now that identifies the outside internet-facing address for your router. But also for your router, you have a home network, and that home network can have a lot of devices. And so you usually, with these home networks, you can't see devices directly. and it's called a so-called private domain. The other private domain, instead versus the 10.0.0/24 subnet network, is also the 192.168 network. And so here you have specialized private domains that allow you to create a network at home and within your network, not visible to the outside world, to the public-facing internet. And so what happens with NAT says, well, how do I get datagrams to seamlessly get forwarded to and from these devices that are on a network on the home side of the router that is hidden from public view? Now, what NAT does is it gives you a translator, and it uses the port numbers on this public-facing IP address, in this case 138.776.29.7. It uses the port number to multiplex to the individual IP addresses on the home side of the network. So let's take a look at what happens here with NAT. And so all of the replacement for outgoing datagrams will happen from this private network domain to the public network. It's going to create a port number on the public side to match that particular IP address on the private side. And so here, the NAT has what's called a translation table, and this translation table is self-populating as communication happens. And so let's say on the private side, you have host 10.0.0.1. It wants to send a datagram to a destination address of 128.119.40.186, port number 80. So port 80, that means it's a web server. And so it creates its own port number because you need port numbers for communication. Let's say this source machine at address 10.0.0.1 chose port number 3345, so-called ephemeral ports, short-lived ports, which are created for you because every connection needs a port number as well. And so we have our source and we have our destination, and it goes into the NAT because this router has an interface that it shares with this private network, the 10.0.0 network, and it goes into the NAT. So the NAT then creates an entry, and this entry is associated with the public-facing IP address, and it creates a new port number on the public side. And so here, then, it takes this datagram and it rewrites it. It says, okay, well, I'm going to replace that 10.0.0.1 IP address with the public address on the public side of the router, 138.76.29.7. I'm going to create randomly a new port number 5001. And so in the NAT translation table, on the wide area side, it says, all right, I'm going to write down the public IP address with port number 5001. And on the local area network side, this private domain, I'm going to write down 10.0.0.1 and port number, ephemeral port 3345. So then on the public side, this datagram is rewritten and it goes out onto the internet, and everyone on the internet that gets this, namely the web server, listening on port 80 at IP address 128.119.40.186, it thinks that this router originated this request message. So when it responds back to 138.76.29.7, port number 5001. Now, of course, when this arrives, it goes into this NAT, and it says, oh, wait a minute, the destination is 138.76.29.7 and port number 5001. So it looks up in that NAT translation table on the wide area side, looks up that port number and says, aha, that is associated with address 10.0.0.1, port number 3345. So it rewrites that and pushes it onto the local area network or home side of the network, and it makes its way to the correct machine. And this all happens seamlessly, this populating of the network address translation table. Now, when you buy a router from Best Buy, this router has not only just the routing function, the store and forwarding, it has DHCP, Dynamic Host Configuration Protocol server running, and they also typically have a NAT system running. And so it's not just routing, even though they call it a router. All right, and so the port number, when you're doing NAT, it means that you can share now a single IP address on the wide area network side of your NAT box and your router you can now share it between a total of 65,535, or 2 to the 16, over 60,000 simultaneous connections to machines on the local area network side. Now, of course, NAT is controversial because routers should only process up to layer 3, and here you have this NAT function on a router messing around with this port number exchange and rewriting in addition to the IP address. Okay, and so with that, we will skip IP version 6, and as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.